In this video, I'm going to be introducing the idea of the definite integral. So what is the definite integral? Well, hopefully we understand at this point that we can approximate areas under a curve using areas of rectangles. And if we increase the number of rectangles, we increase our approximation. We get closer and closer to the real area. And if somehow we could increase the number of rectangles to an infinite amount of rectangles, then we would actually get a very good approximation. In fact, the definite integral is saying exactly that. So here is one way to define the definite integral using a limit and a summation. This is saying that if I have n number of rectangles, starting with one rectangle, and I approach an infinite amount of rectangles, and I find the area of each rectangle, that's all this is, the height of the rectangle times the width of the rectangle. So if I have an infinite amount of rectangle areas, then I can get real close, if not exactly, the area under the curve. And so what happens is this becomes the notation for a definite integral. So we see our integrand symbol. Below that, you'll see a value, and above it, you'll see a value. The number below is called the lower limit of integration, and the above value is called the upper limit of integration. We have our function that we're integrating with respect to the variable of integration. Another part of the definition that we need to know is that continuity implies integrability. So we can integrate even if the function is not differentiable. So when we were talking about how something needed to be continuous and the limit needed to exist in order to find the derivative, this is not quite as specific. This is just saying if we know the limit exists, because that's part of the definition of an integral, and if it's continuous, then all of that is implied and we can integrate. And so, for example, we could think about velocity. If our velocity function is an absolute value function, that means it's got a sharp point at t equals 0. We can find the position. We can integrate that sharp point. We just can't derive it. So we can't find the acceleration, but we can find the position. So just a slight discrepancy there. All right, that leads us into the fundamental theorem of calculus. And here's what that describes. If we know the function is continuous on a closed interval, and we can find the antiderivative on that same closed interval, then this is what the definite integral becomes. We're going to evaluate the antiderivative at the upper limit, and we're going to evaluate the antiderivative at the lower limit, and we're going to subtract those two values in that order. We no longer need the constant of integration, and here's why. If I'm subtracting, if I was to give both of these a constant of integration, I have f of b plus c minus the entire f of a plus c. So we got to distribute that minus sign. So when we subtract c from c, our constant of integration goes away. So when we're describing definite integrals or evaluating definite integrals, we no longer need that constant of integration. So here's what we're going to do when we evaluate. We are trying to find the exact area under a curve when we do this, so always keep that in mind. We're going to find the antiderivative of the function first. We're going to evaluate it two different ways. We're going to evaluate it at the upper limit, and we're going to plug in the lower limit to evaluate. And then we're going to make sure we subtract those two values in this specific order. There are some properties for evaluating definite integrals, and you should keep those in mind. I've attached on my website some of those properties. Take a look at those. But we'll have some examples to practice with right here. So there is a constant function rule for integrating. And that is basically saying that if I have a constant function, I know I have a horizontal line. And if I find the area underneath that horizontal line, well, I'm just finding the area of a rectangle. So all I need is my height and my width. Well, the function value is the height of the rectangle. So in this case, 3 is going to be the height of my rectangle. And if I just know the width or the x-axis interval length here, then I can find the width. So if I'm going from 1 to 4, from 1 to 4 would be my width. So that length is 3. So I have a 3 by 3 rectangle. That's actually a square, huh? And we can find the area by multiplying length times width. So it's just 9. So the shortcut, whenever we're integrating a constant function, is find the difference in your limits of integration and multiply that by the constant function value. Just the area of a rectangle. All right, let's get a little bit more complicated. Here, we're going to find the antiderivative first. That's our first step. So the antiderivative of x cubed is x to the fourth divided by 4, or 1/4 of x to the fourth. We're going to evaluate that using the upper limit. So we're going to plug the upper limit into that. And then we're going to subtract the antiderivative evaluated at the lower limit. So we're going to plug the lower limit into the function and just subtract it in that specific order. Evaluate, and you get your exact area under this graph. So we can visualize it. We can see what x cubed looks like from 1 to 3. And we're actually finding the area of this spot right here. And it's exactly 20 units squared. So always keep in mind that what we're doing when we evaluate a definite integral is find the area under the curve. Eventually, we'll talk about more applications of it. So in these two examples, I'm going to skip the graph. Just keep that in mind, and we'll just focus on the process. We're going to find the antiderivative of this first using that sum and difference rule. So find the antiderivative of the function. Evaluate that at 2. So plug 2 in. Evaluate it at 1. And subtract in that specific order, f of b minus f of a. And simplify. And eventually you end up, hopefully, with negative 2/3 in this example. So that represents the area under that curve from 1 to 2. One more time. Sometimes you may want to rewrite before you find the antiderivative or shift any constant coefficients out to the front. So finding the antiderivative of the square root of x times 3. So the antiderivative after we simplify becomes this. We're going to evaluate that. We're going to plug 4 in. And we're going to plug 1 in. And we're going to subtract it in that specific order, simplify, and hopefully end up with 14. Again, the area under this curve. Let's do an example with a trig function. So same steps. We're just going to evaluate the antiderivative first. The antiderivative of secant squared is tangent. And then we're going to evaluate it at the upper limit. So the tangent of pi over 4 is 1. And evaluate it at the lower limit. So the tangent of 0 is 0. And 1 minus 0 is 1. So if we graph secant squared in between 0 and approximately pi over 4, what we're doing is finding the area underneath this graph in between the graph and the x-axis. So all of this area right in here. And that turns out to be exactly 1. It's kind of nifty. And one more time, just a different way of asking the same question. Find the area of the region bounded by the graph of the function between the x-axis and two vertical lines. X equals 0 is right here, and x equals 2 is a vertical line right here. So we know our interval is between 0 and 2. We're just going to find the antiderivative of this function and evaluate it at our upper and lower limits. Our upper limit would be 2, lower limit would be 0. And eventually we get 10/3. So there's an introduction to the definite integral. Make sure you understand how to evaluate it and what it represents.